In the first part of this chapter, we finished talking about compilation and pure interpretation and hybrid implementation systems. In the next slides, we will explain all these three different types of implementation methods. But before we go to talk about compilation in details or pure implementation, interpretation or hybrid implementation systems, I would like to show you the computer layered system, which is shown as the applications, the programming language, different programming languages as application installed on top of the operating system, and the operating system and the language implementation are layered over the machine interface of a computer. So if this is a computer, then you will see that the pair machine, this this part here is layered under the macro instruction interpreter. So the macro instruction interpreter is on the kernel itself, which is the heart of the computer, the heart of the computer operating system. Then the operating system components layered over this interpreter. Then these languages, different languages like C++ and C compiler and all these compilers, these are programs which are compilers for these languages that you see here outside. So each one of these programming languages, whether it is object-oriented or procedural, they have their own interpreters or their own compilers. Some of them they have interpreters, some of them they have compilers, and some of them they have assemblers. For example, the visual assembly language, it has assembler, while the command operating system, it has an interpreter. And Ada programming language, they have compiler, C, C++, and C Fortran, they have compilers. Lisp programming language, it has an interpreter. So whatever they have, if they have interpreters or compilers or assemblers, these programs are layered on top of the operating system. Now this is the way that the von Neumann structure is depicting, because assume all these programming languages are installed on your computer. So each one installed in your computer, it has its own program that help translating the source language into machine language using either a compiler or interpreter or assembler. The compilation process, which is simply is a translation of high-level programming language, which is a source language, into machine code. We know that the computer doesn't know any other language. It has only one language called machine language, which is the digital language, the language of binary, or the binary digit language. So simply the computer know only two numbers, these zeros and 0 and 1, such that 0 is an off signal and 1 is an on signal. So combination of zeros and ones, they make what we call byte. Each one of them is a bit. 0 is a bit and 1 is a bit. So they call it bit. Why bit? BIT, because bit for binary digit. So they use the word bit for it. So if you have 8 bits, combination of zeros and one, they make 1 byte. So if you have you need 2 bytes. If you have 2 bytes, then you need 16 bits and so forth. So each character, or each number, each symbol in the computer has a representation of 8 bits. The computer has 255 characters and numbers and symbols. Each one of them has this combination of zeros and ones, and you can find that in the Ascii table. The Ascii table is American standard code for information interchange, which you can look it up in the Google and try to find Ascii spells like this, ASCII. If you look for it in Google, then you'll find a table. You will look at the representation of numbers and characters together. So anyway, we talk about what about machine language. We said that the computer only know one language, which is a machine language, which is a binary language. So what does the compilation do? The compilation is a translation of high-level language, which is the source code of our programming language, like in Java or C++. It translates it from this source code into machine code so that the computer can understand it. It has slow translation because it has to go over all these characters and numbers and symbols and translate them into binaries. But it has fast execution compared to interpretation. But this one, although you don't see it, it is all behind the scene. But basically, it has several different phases or steps. These are called lexical analysis, syntax analysis, semantic analysis, and code generation. In this order, because the lexical analysis, it converts the characters in the source program into lexical units. So it actually like chops it, like you have a watermelon, and then you like actually to cut it to small pieces to give it to your guest. What do you do first? I mean, in order to cut it to small pieces, what do you do? I would think first you might need to cut it into two, right? Two big parts. Then take one part and leave the other one. This half you cut it into smaller chops, right? Smaller chops, like maybe 6, 7, 8 of these pieces from this half of a melon. Then what do you do next? You take one of these pieces and then cut it into small pieces and take the skin out of it. Then put it in a plate, and you keep repeating that. So simply, lexical analysis is to convert characters into source program into lexical units to make it like small blocks. Then this syntax analysis will transform these lexical units into a pairs tree, like make up small pieces of it, which represent what is called syntactic structure of the program. This will be responsible for finding errors, for example, and stuff like that. Same like you have these small pieces and you would like to take out the seeds from these melon pieces and make it, just easy for people to eat. So the syntax analysis will do this part. Semantic analysis will generate the intermediate code. Intermediate code, that means it's not the final code, which is the semi-final code that will be given to the code generation, which will lay the rest of the process. It's gonna translate it into machine code, and then machine code is generated, and the executable program is executed or created. In such a case, the program is going to be ready for running. So the compiler process will actually look like this picture, as you could see. Here you have, for example, 3 files. Each file has a source file, source code, in whatever language that you can imagine. Then it will take it to the compiler. The compiler will create the object files. Each program will have a different object file created. Then if there is any libraries stored, properties, saved description for the program, or preprocessor directives that will going to be added to the program, this is going to be added through what is called linker. The linker, which links the runtime library files with the object files, and then create the executable program. The executable program that is usually is application with .exe, executable program that is actually you can run. So once the program is compiled, it is going to be running as an application. So this is actually compilation process, how it goes into these steps. It can be further explained by this. Look at top and bottom. What do you see on top? On top you see a source program. At the very bottom you see results. But how do you come to this result? You go through lexical analyzer, syntax analyzer, code generator, and intermediate code, and then code generator. These are the 4 that we just talked about here: lexical analysis, syntax analysis, semantic analysis, and code generation. This semantic analyzer is called intermediate code. So this is the one that the one in the middle here. So what happens is that as we mentioned earlier, the lexical analysis or the analyzer in the compilation program will take it to the syntax. We will take this lexical units as chops, as big blocks, to this program, which is called syntax analyzer within this compilation program. The symbol table is a table of symbols, that some of these symbols that cannot be sent directly to the syntax analyzer, it can be also sent to the symbol table to be stored here. And some of these symbols also cannot be sent immediately to the intermediate code or to the semantic analyzer. Then it can be sent here to the symbol table. The symbol table will actually sort them out and then take them to this intermediate code. The intermediate code will either optimize the program or can also send it to the code generator immediately. This intermediate code, after being sent to the code generator, then it is ready to actually be translated to a machine language, so that if you have any input in the computer, whether this input is coming from a file, or this input is coming from a keyboard, or this input is coming from the program as hard coded, then the machine code will be able to adjust that and send so the same code as a machine code to the computer, and then this will create this application ready to be executed. Then this one will give you the result at the end. So this is actually the steps of this 4 different steps. This is the first one, lexical analyzer. Second one, syntax analyzer. Third one, semantic analyzer or intermediate code. And then the last one is code generator. And this is how the process is done through a computer system. There is some more terminology that I would like to talk about in this respect, which are the load module and linking or loading. The user and the system code, the user code and the system code can actually be loaded to the program through a program called loader. So the load module or the load function it has an image, or it has like kind of reflection inside the program of some languages that help the user code and the system code to come together and be loaded in the program. This is similar to the operating system. When you actually start up operating system, you see the operating system when you start it. When you switch on your computer, what happens? It doesn't just you know it doesn't just be ready immediately. It takes several minutes, right? If you restart your computer or you shut it down and you start it again, then it takes a lot of time in order to come up. What happens here is that a lot of programs are loaded up in the memory through this program called load module. And this is actually especially in operating systems more than programming languages. So this is done through a process called linking and loading. So linking and loading is the process of collecting the system program units and linking them to a user program. So what happens when you restart your computer? Because when you restart your computer, for example, what happens is that this software on which the operating system is created, whether a Unix system or a Linux system or a Windows system, it needs to have a lot of different things working. It needs to make sure that the keyboard is connecting to the operating system. It needs to make sure that the mouse is connecting. It needs to make sure that the screen is connecting properly. It makes sure that the other devices like printers or scanners or anything connecting to the computer is actually linked and loaded together with the operating system loader. So this linking and loading program is the process of collecting all these system program units and link them together for a user program to work. So this is additional compilation terminology that you might need to understand. All right, what is this concept? It is very important to know about what is called von Neumann bottleneck. What is von Neumann bottleneck? Bottleneck here means, in Arabic, we call it عمق الزجاجة, but in this programming concept, it is a jam or a restricted access or a trailback or hold up. We call it jam or hold up or freezing, something like that. So this is von Neumann bottleneck, because the connection speed between a computer's memory and the processor always is determining the speed of a computer. So the speed of the computer will be determined by the processor and the relationship between the memory and the processor. So sometimes these instructions that you feed on the computer can be executed faster than the speed of the connection. If this happens, if the program instruction are executed much faster than the computer speed connection, then this will create what we call bottleneck. So simply, a bottleneck is one of the limitation of the speed of computers, and this will actually, what happens sometimes, you'll find your computer freezing. Because why freezing? Because the instructions are executed faster than the speed of your connection. The connection speed of your computer is not going to match the instruction. For example, you are clicking here, click here, right click here, and try to open this program, and you do a lot of instructions. So you're actually doing a lot of instruction at the same time. In 1 minute, you clicked like 700 times. So the computer cannot adjust these actions. So what happens? Sometimes the computer freezes, or the language that you are using freezes. Sometimes you have to do what we call killing the process. Sometimes, let me show you what I mean. Killing the process, guys, like this. You press Control Alt Delete, and then when the screen comes, you click in Task Manager, and then in the Task Manager you select the program that is freezing, because you'll find the process that is making the problem. So for example, there is a lot of processes here, and you can actually see the memory usage and the CPU usage, and which one is actually it has, for example, this active presentation, it has very high, it used to be very high, now it is moderate, because I've been using it so heavily. I'm right now using it to record this video. So that's why, and other programs are very slow because they are opened before, and they are not taking that much memory on the computer. But sometimes if something is freezing, you have to click on it, like this one for example, and right click, and then you can end this task or kill it, right? You can stop it from here if it is freezing. Now you see the numbers changing here on the percentage of the network. This will determine the speed and on this device. So what I'm saying is, what I'm talking about, the von Neumann bottleneck, and then the von Neumann bottleneck is simply the instructions are executed more faster than the speed or the connection speed of the computer. This results in this freezing or jam. Let us talk about the pure interpretation. The pure interpretation, in pure interpretation, unlike compilation, there is no translation. So what happens is that a statement is explained, or there is no full translation. The translation is done through statement by statement. Through this process, because the computer will finish one instruction and go to the next instruction, then finish it up and then go to the next instruction, and so on. So it is easier implementation of the programs. So, and then also runtime errors can easily be displayed, but it is slower execution, 10 to 100 times slower than compilation. Let me go back, guys, and talk about the Melon example. In the Melon example, there's two ways to cut the melon, right? Okay, there is many ways, but basically sometimes people use two ways. The first way is to cut this watermelon into two pieces through the length, not the width, and then take one of the parts and put it on the cutter on the board bottom down, and then bring a knife and then cut 1, 2, 3, 4, 5, 6, 7, 8 pieces, and then you take them all, cut them all together in one, or 4 of them in one handle, and cut them into small pieces. This is one way. The other way is to cut it into 2 pieces, then cut one small piece, and then take that small piece and cut it into small pieces and remove the skin. Then take another small piece, cut another small piece, and take it into your hand, and then cut it into small pieces again, and repeat this process. I'm not sure if you understand my example, but usually what you do is that you do it a small piece by a small piece by a small piece by a small piece. You don't actually do do it all together, like multiple pieces together. No, you do it one by one. You do it one by one. This is what is actually referred to as interpretation in programming, in which instructions are done one by one. The computer finishes one instruction, then goes to the next, and then gives the result of it. Then go to the next one, execute it, translate it, interpret it, and bring the errors and everything, and then finish it and give the result, and then go to the next one, and so on. So it is slower execution than compiled programs, and sometimes it requires more space. So now, rarely used for traditional high-level language. So interpretation is not used for C++ or Java or something, or C# or something like that. It is actually used for scripting language like JavaScripting and PHP and Python and stuff like that. So interpretation process is just like this, a symbol like this. The source code sent to the interpreter. If you have input data, outside input data, then it is going to be added to this program interpreter, and then it gives you the result. So compare this pure interpretation process to the previous compilation process. So let me just go back to the compilation process. This is the compilation process. It has 4 steps: lexical analyzer, syntax analyzer, and then semantic analyzer, and then code generator, and then the result. This is the source code, and this is the result. But here you have the source code, and then the result. In the middle, you have just interpreter program that it doesn't connect or load or link or give you any intermediate code or pre-use code. Another or a third type is called hybrid implementation system, which is actually a compromise between compilation, pure compilation, and pure interpretation. In this program, in this hybrid, hygiene hybrid between interpretation and compilation. So this program, simply in this type of programs, a high-level language program is translated into intermediate language that allows easily interpretation. First is going to be translated into intermediate language so that it can be easily interpreted. It is actually faster than interpretation, but slower than pure compilation. So it is something between them. We use it for parallel programs. These parallel programs are particularly compiled to actually get the errors out of it before being interpreted. And also some implementation of Java can be done through hybrid. And because in interpretation, simply after that bring the code interpreter through runtime systems, especially in some applications like Java virtual machines, for example. So this hybrid implementation process looks like that. So here, the source program, and this is the result. Alright, so what happens here, you have lexical analyzer, which send the lexical unit to syntax analyzer, and then intermediate code, and then it will send it to the interpreter to make it ready for making the executable program for results. So this is a hybrid program. So it has also 4 different phases, which is lexical analyzer, syntax analyzer, and then intermediate code, and then interpretation, which is almost similar to pure compilation, but it is 3 steps of this compilation plus the interpreter program itself. The last one is called just in-time implementation system, which is short name for it is JIT or JIT. This is actually used to translate programs to intermediate language. Then after that, it will compile this intermediate language of subprograms into machine code and make them like functions before they are called to be executed. So what happens is that the machine code actually is going to be kept in some subsequent calls, ready to be called by a program in order to be executed. So it is going to be actually stored temporarily in the system before it is called to be executed. It is basically used for some Java programs, or .NET languages also can be done through JIT systems. So JIT systems are good interpretation systems, and sometimes people call it delayed compilers because it is not fast as compilers, but it is not as slow as interpreters. It's kind of similar to the hybrid. The last thing that I would like to talk about here is the preprocessors. What is a preprocessor? Preprocessor simply are some code that is generated from another file, not from within the same language. It could be in a different language, or it could be in the same application, but it is stored separately. So a preprocessor program simply is done before the program is compiled. Okay, it is a program that is going to be called or executed before even the program, before the language program is compiled. I have two examples here, like include and define. These are some preprocessor directives that are used in C or C++. Let me show you here one example in my C program. So for example, here in this program, I have this part is called preprocessor directive because it's a header file. I mean, when you say include IO stream, you mean before you come and compile this part of my program, include input output stream file, header file. If you search for IO stream, it is a file. It is a file stored in this computer application. So it has a lot of different properties. It has description, it has functionality, it has all input properties and output properties. So it is a file. It is a big file. It's not a small file. So when you say include it, that means you are going to, or you are telling the compiler to execute this one first before you compile this. All right. So also like define. So if you have like define here, define is one of them. If you'd like to define a message, for example, define a message as okay, good night, for example. All right, I like that. So I'd like to define it. So this is going to be compiled and executed before the program goes here to this line, before it goes here from line 4 down. This is from the library, from the standard library system. But if you would like to get, for example, this program executed, now let me see. I can actually, after I define this message as here, after I define this message, this is my line there. Hello, welcome to programming languages. So I would like to actually display that preprocessor directive define. I can use an output statement to display this message to the screen, which is defined here by this preprocessor directive. So now I can display this message on my application. So what happens is that here, anything that you add before this, it is part of what we call preprocessor macros or preprocessor instruction that is commonly used to specify that the code from another file or from another place to be included in this compilation process before the program is compiled. So a preprocessor processes a program immediately before the program is compiled to expand this embedded code. The embedded code that is like the example that I gave you earlier on this C++ example. Let us just finish up by talking about this programming environment. So there is a collection of tools used in software development like Unix and Microsoft Visual Studio.NET and also NetBeans. There is a lot of environment that people use for software development. So Unix is very old operating system and tool collection. So sometimes people use it as graphical user interface through CDE and CDE development environment and KDE or the GNOME development environment, or we call it GNOME here, GNOME or GNOME, that runs on top of this Unix. All these are graphical user interfaces for Unix. Microsoft Visual Studio.NET also is very complex environment. It is used to build some web applications also and non-web applications by using .NET framework. NetBeans also is related to Visual Studio.NET, and it is actually used to create application especially for Java. So this is it. The summary for this chapter is to study the study of programming language is very valuable for a number of reasons. We did mention them earlier in our first video. Increase our capacity to use different constructs will enable us to choose languages more intelligently and makes learning new languages easier for us. And then we did talk about most important criteria for evaluating programming languages, which include 4 different criteria. These are readability, writability, reliability, and cost. We explained them in the first video as well. And then we said major influences on the language design have been machine architecture and software development methodologies. Then at the end, we did talk about the major methods of implementation program language like compilation, peer interpretation, and hybrid implementation, which we just finished them in this video. And this one concludes chapter 1. Thank you.